Hello, class. Welcome back. This is lecture 9. Today we'll be talking about the P series. So this is another sort of classification of series that we'll do so that we can figure out whether a certain kind of series converges or diverges very quickly and easily. So here's the idea. We've already done one of these actually. So we've seen that this guy diverges. It was called the harmonic series. But what about if I change the power of n? So for example, if I made this be like cubed or something, or I did a square root. Remember, a square root really means a 1/2 power. So what we want to think about is all of the possible choices for this number here. So like that's a choice of 3. That's a choice of 1/2. This even has a secret 1 here, of course. If you don't put any power, it means a power of 1. So we want to think about all of these series sort of at the same time and see if we can figure out when do they converge and when do they diverge. So what I can do is just create another variable. I guess it's called P typically, hence the name of the series is called the P series. So we want to know, when does this thing converge or diverge, aka what values of P make it converge or diverge. And like I just said, we already know the answer for P equals 1. It'll diverge. That's up here. But what about all the other numbers? So let's see if we could solve this question for all of the series of this form at the same time. So this is called a P series. Okay. Just real quick, this is different from a geometric series. Different. This is a very common mistake, is to mix these two up. So what was a geometric series? So the difference was, it was a number to the nth power. So you're just adding up powers of the same number. And we figured out like R has to be between 1 and -1 for this to converge. But what's this? This is, the power is not changing like it is down there. The power is staying the same. What's changing is the number that you do to that power. Okay, so this is a P series, and then the other one is a geometric series. They look very similar. Geometric series we already figured out. P series is what we're figuring out today. Okay, so let's see how we can do this. It's pretty rough. So just try to stick with it. It is kind of hard, but we'll do our best. Okay, so we're going to look at the partial sums, but we're going to put a little spin on it. Instead of going up to k like we normally do, we're going to go up to 2k plus 1, and this will come in handy later. So for example, S1 is 1 over 1 to the p. S2 is 1 over 1 to the p plus 1 over 2 to the p. And SK is this, but we're not going to really deal with that. We're going to go past that one. So if we keep going to s to the 2k plus 1, what's that going to look like? Well, it's going to look the same, except it just ends a little bit further. So it ends at 1 over 2 k plus 1, and then that's to the p power. Okay, so we're going up to there, and the payoff will be revealed soon. So what we want to do is we want to break this into evens and odds. So the first one, well, that's just 1. So let's just take that separately. But after that, we're going to rearrange all the terms. So we're not adding anything new or taking away anything. We're just rearranging. So that 1 is staying in the front, but after the 1 over 2 to the p, there is a 1 over 3 to the p, but we're going to move that to later. And instead, we're just going to have 1 over 4 to the p. And then we're going to skip the 1 over 5 and do the 1 over 6. And what we're doing is we're doing all of the even numbers. And so the last even number is going to be 2k, because the last number is 2k plus 1. So what's right before 2k plus 1 would be 2k plus 1 minus 1 would be 2k. So that's the second to last number, and it's the last even number down there on the bottom. So we're grouping up all the evens, and then we're going to group up all the odds. So 1 over 3 to the p, 1 over 5 to the p, and so on like that. And then the last odd number is 2k plus 1, because remember, 2k plus 1 is automatically odd always. So this is just a little rearranging trick. We haven't changed anything. But what we're going to do now is something we've done before, which is realize, like, okay, it's hard to figure out some sort of exact formula. So instead we say, like, can we make this be less than or greater than something else? And then that something else will be easier to deal with. So here's what we have to notice. So how do, we're going to compare these things to each other. So how do those compare? So for example, what's bigger, a third or a half? A half, right? And then let's compare the next two. So what about a fourth and a fifth? Which one's bigger there? 1 over 4 is bigger, right? It's always going to be the smaller number. That means the same color, sorry. It's always going to be the same. The evens will always be the bigger one. So if I compare 1/6 and 1/7, same idea, because the even number is smaller. So these are always bigger. So then what's the last one? This one and this one. So 1 over 2k plus 1 is less than 1 over 2. Sorry, 2k. Okay. So we have that. So then what I want to do is compare the entirety of this thing to the entirety of this thing. So which one is bigger? Well, every single even one is bigger than every odd one that it corresponds to, right? So that means if I add them up, of course, I haven't done anything with the p power yet, but that will not be so bad to put in. But if I add them all up, then the even ones will be bigger, because every single even one is bigger than every single odd one. So that's true. But of course, you can just power these guys up, and everything will work exactly the same. So let's just put that in there as well. And then the idea is, so this SK, S2K plus 1 that I'm looking at is smaller than, if I keep the first part the same, so the 1 doesn't change, the evens don't change. But then I replace the odd ones with something bigger, right? The even ones are bigger. Then I can say that this thing gets bigger. So I can just replace it with another copy of the even ones and say this. But then that's just 2 of the same thing. So you could say it, look, it's really this. 2 of the same thing just means you add up 2 of them. So you put a 2 in the front to multiply instead. And it looks nicer like that. So now for another devious trick, what we're going to do is rewrite this guy as a sum of its own. So how can I think of this? Well, I can think of it as 1 divided by even numbers added up together. So I could think about it as 2 times something. But I don't want to use k because k is really the last number that I plug in. So I'm going to use a new variable, I'll call it I. And if I start at 1, then that is exactly the same as this thing in parentheses here, right? I'm just using a different letter as the index. But if I actually write them out, it's exactly the same. Oh, I forgot the p power. So like if I plug in 1, I get 2 to the p. If I plug in 2, I get 4 to the p. If I plug in 3, I get 6 to the p. And I get to the end, I plug in k, I get 2k to the p. So this is just shorthand for what I've written in parentheses. And so now I'm going to replace this here with what I just figured out. And then I'm going to actually factor out the 2 on the bottom. So the idea is that if you have the power of p on the 2 times the I, you can think of it as 2 to the p times I to the p. And then this thing does not depend on the index. It's not changing. So it's really just a constant. And so you can take it out just like you could if it was like just a 7 sitting there, because it's just a number that doesn't depend on the index that's being multiplied. So you can factor it out. And then you're left with this. But again, this sum is really something familiar, just with different letters. So if I write it out, it's just 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, all the way up to 1 over k to the p. That's really just sk. That's a partial sum up to k. I've just changed the letters. So normally you would, it would look like this. Oops. It would have looked like this. But the point is, it doesn't matter what you use as the index, it still is just sk. It's just a partial sum up to the kth term. And then these guys, you have the same base, so you can just subtract the powers to simplify that. and then we get this. Okay, so long ago, what we started with was this thing. So now let's zoom out and just say what we have. So we have S2K plus 1. We don't know a formula for it, but we know that it's less than this other thing. Okay, so that's where we want to be right here. And then a long time ago, I wrote this. So SK is just adding up to K terms. And then S2K plus 1 is going to be bigger because you're just going further in the terms. You're just adding more things. So now what we're going to use next is the fact that this is bigger than just SK. So then down at the very end where we are, if I replace SK with S2K plus 1, it gets bigger because I can just make a chain of greater thans or less thans, as long as the thing that I chain with it gets bigger. So this is true. And then what I can do is now I can actually solve for this by just moving them to the same side. So now if I subtract the terms that have this S2K plus 1 in them to the same side, then I can factor them out. And then I can divide. And then what's going on is I never did figure out a formula for S2K plus 1, but I figured out something that it's less than. And that's good enough because what I need to do is take a limit. Okay, so let's see. So this will depend on what P is, which is of course what we want. So there are a couple cases here. Well, what happens if P is just 1? Well, we already know the answer. And luckily we know the answer because this will not help us at all, because we'll get 1 over 2 to the 1 minus 1, which is 1 over 1 minus 1, which is 1 over 0, which is bad. So if P is 1, then all the work we just did is useless. But luckily, we already know the answer because we did it a different way a long time ago. We already know the answer to this if P is 1. We already know it diverges. Okay, so let's think about what happens if P gets a little bit bigger than 1. Because 1 is like the really terrible number for P. But maybe if it's a little bit bigger, it'll work out. Let's do that. So what happens if P is bigger than 1? So then, what does this look like? Well, what's this going to look like, first of all? So if P is bigger than 1, then what does that mean? That means 1 minus P will be negative, right? Because I'll be taking away more than 1 from 1. So if P is like 2, for example, it'll be negative 1. And what happens if you have 2 to the negative power? Well, then it's going to be 1 over 2 to the same power. So the point is you're going to get some sort of fraction less than 1. So then what does this look like? Well, if this guy is a fraction less than 1, then when you do 1 over 1 minus that number, what's going to happen? Well, this will be a positive number because it'll be 1 divided by 1 minus a fraction below 1. So it'll just be some positive number. So the point is that you'll just get some positive number. So what that means is that S2k plus 1 is always going to be less than some positive number. And so when you take the limit as k goes to infinity, it'll be it won't go to infinity because it's bounded by this positive number that we don't know what it actually is. It just depends on what p is. So for example, if p was 2, you could figure out exactly what it is if you want. Then it would be 1 over 1 minus 2 to the 1 minus 2, would be 1 over 1 minus a half, would be 1 over a half would be 2. So then this would be saying that the partial sums is always less than 2. And so when you take the limit, it definitely can't go to infinity. It's going to be less than 2, in fact. I should just say it'll be less than that same number. Okay. So the point is that it'll converge because the partial sums are bounded. Okay, so this guy, what we figured out is that this guy converges if p is bigger than 1. So that's the big takeaway that we need right now. And so immediately you could just like do an example. This guy converges by, just say by p series. P equals 4. Is 4 bigger than 1? Yes. It doesn't have to be way bigger than 1. It can just be a little bit bigger than 1 and it still works. N to the 1.1 still converges because p equals 1.1 is bigger than 1. Any amount bigger than 1 at all will put you in the same situation where the partial sums are less than a number, are bounded, so the limit will converge to a number. Okay. So what about if p is less than 1? So we know what happens if p is equal to 1, it diverges. If it's bigger than 1, it converges. So now let's switch to what if p is negative, or sorry, not negative, just less than 1. Well then, 2 to the 1 minus p, we have the opposite situation. This is going to be 2 to a positive number now, because you're subtracting something less than 1. So then 1 over 1 minus 2 to a positive number, which is what we're looking at, will be 1 over a negative, because what you're doing is you are doing 1 minus something bigger than 1. So it's going to give you a negative on the bottom. So this will be a negative number. So then this doesn't, now what this means is, so when you have p being less than 1, then this bound does not apply. Does not actually work. And so what will happen is that this thing will diverge because these guys are not bounded anymore. So their limit will go to infinity. So now just very quickly, you can do these types of problems very quickly. Now you can say this guy, if I do like 0.75, that will diverge because P is 0.75. This is a P series, that's less than 1. The only tricky one is like things like this. The square root, you have to remember that that's actually a 1/2 power. And so this is still a P series with P being a half, which is less than 1, so it'll diverge. So that's like the trickiest it can be. The other tricky part is accidentally mixing this up with things that it does not apply to. So it's very specific. It has to look like, well, it's called a P series. It has to look like 1/n to a power. Converges if P is bigger than 1, diverges if P is less than or equal to 1. So 1 is the exact boundary at which it changes from converging to diverging. And then the other thing is to note, we did not actually calculate what this adds up to. So we didn't calculate what it actually converges to when it does, I guess. So when P is bigger than 1. So we avoid the problem of ever calculating it because that's too hard. And we just say what it does, converge or diverge, when it does it without actually calculating what it converges to. Okay. And then of course, so you could use tricks to do things like this. If you change the starting number, it can still work. So this will still converge because this guy converges, the actual P series for P equals 3. So why does the first one still converge if this one does? Well, it's because they only differ by a finite amount. The first guy is missing, it's missing just a couple terms. It's just missing these ones. That's just some finite number. And so if this one converges, then this is just a little bit less than that. So it'll have to converge too. Same idea for diverging. So if you start at here and you do 1/square root of n, this will still diverge because the actual P series where it starts at 1 diverges. So again, I want to stress what you should do is you should compare to the geometric series and make sure that you can tell the difference. And make sure you can tell when you see something which is which. So for example, this guy is geometric, but this guy is a P series. P is 4/7, that's less than 1. So it'll diverge. This is a geometric series where R is 4/9, that's less than 1. And that tells you it converges. Okay. The very general way to think about all this, the P series stuff, let me scroll back up here, is basically you need big powers of P, because if it's too small, like if it's 1, so if you just have 1 power of P, which is the harmonic series, like this, then the numbers that you're adding up, they sort of shrink too slowly. So it diverges. You end up adding too big of numbers, and they add up and go to infinity. And if you just go a little bit past 1 to like 1.1, now suddenly it's big enough. It shrinks fast enough. Now these numbers actually shrink fast enough. They shrink fast enough so that when you add them up, it'll converge to some number, even though we don't know what the number is. And the only difference is this power just needs to be a little bit bigger than 1. 1 is not big enough. Okay, that's it for today. See you next time.